Good morning, everyone. Our first speaker today is Supriyo Dutta from SR University, and he will talk about constructing cospectral graphs using partial transpose.
Thank you very much for introducing me. We can use partial transpose to construct a cospectral graph that I shall discuss with you in this meeting. So this talk is distributed into several sections. First of all, I shall start with some basic ideas on graph isomorphism. Then we shall define a particular types of graph where we can define partial transpose. Then we shall use this idea of partial transpose to construct cospectral graphs. So the graph isomorphism problem is a well-known problem in mathematics and computer science. So we have two graphs. A graph isomorphism is a bijection from one graph to the another graph with the particular property that if we have an edge in the graph 1, then if and only if there is another edge determined by the graph isomorphism. So question is whether two graphs are isomorphic or not. This problem was attempted from multiple directions. One was the fact that if two graphs are isomorphic, then they have same spectra. So if we can study the spectra of the graph, then that may give one solution to that problem. That was an initial idea. So there are some matrices. There are a few matrices which eigenvalues we study in spectral graph theory. Adjacency matrix, then Laplacian matrix or signless Laplacian matrix. So Laplacian matrix is just the degree matrix minus adjacency matrix. And in case of signless Laplacian matrix, it is degree matrix plus adjacency matrix. Now, when we have two graphs, if they are not isomorphic, it may be happen that they have a same eigenvalues. But if the eigenvalues are different, then definitely those two graphs are not isomorphic. These eigenvalues comes from either adjacency matrix or Laplacian matrix or signless Laplacian matrix. And now the target is to find some graphs which are not isomorphic, but they have equal sets of eigenvalues. This question was first asked in chemistry in 1956, and after that there are many such examples found where those graphs are non-isomorphic, but they have same sets of eigenvalues with respect to different matrices. So several such examples I construct here. For the first two graphs are non-isomorphic, but they have same eigenvalues with respect to their adjacency matrix. In the second one, this is also a pair of non-isomorphic graphs, but they have equal sets of Laplacian eigenvalues. And this one, the last one I consider here, these two graphs are non-isomorphic, but they are signless Laplacian eigenvalues are same. Now we shall proceed to section 2, where we shall define the partial transpose on the graph. Here we are partitioning the graph. We are assuming that the graph has m into n vertices, where m and n are two natural numbers. We are partitioning the vertex set into n equal parts. Each of the part we are taking m number of different vertices. Suppose in this figure at the end of the slide we have different vertices. Vertices are arranged in horizontal and vertical directions. So V1, capital V1, this contains these vertices V11, V12, V13, etc. The vertex set capital V2, it contains the vertices V21, V22, etc. So when we have distributed the vertices of the graph in such a way, then the edges in it will also be distributed in three different categories. First one are the horizontal edges. So here are some edges, suppose between V32 and V33. This is a horizontal edge. Also V11 and V12. This edge is also horizontal. Also there are some edges which are vertical, such as V21 to V31, also from V13 to V23, etc. And there are some edges which are neither horizontal nor vertical, they are tilde edge, such as the edge from V22 to V1n. In this way, we shall partition this graph. Now, this will give us several subgraphs. These subgraphs will also be useful for us. Suppose here for the vertex set V1, there is an induced subgraph which contains all the vertices in V1 and the edges which join two vertices inside V1. This I have drawn here. Also, suppose we have considered two different vertex partitions. One is Vi, another is Vj. We shall consider all the vertices in Vi and Vj. Also, the edges whose one end is in Vi and another end is in Vj. This we define in this way. So that will be a bipartite subgraph. So these two subgraphs will be useful. Now, when we have distributed the vertices in this particular manner, then the adjacency matrix will also be divided into different blocks. So, corresponding to the vertex set V1, V2, etc., the adjacency matrix values will also be changed. It will give us one block matrix. So here the block A11 will give us the adjacency matrix of the subgraph induced by the vertex set V1. Similarly, A22, this will give us one adjacency matrix corresponding to the vertex set V2. If we take any non-diagonal block and its corresponding Ji term, suppose A12 and A2i, then they will form one matrix like that, and that will be an adjacency matrix of the bipartite subgraph containing the vertex set Vi union Vj, whose edges has one end in Vi and another end in Vj. So when we partition the graph, the adjacency matrix will also be partitioned. Now, if we have any binary matrix, 0, 1 matrix, then also we can construct a bipartite graph from that. And based on that binary matrix, we can change some portion of the graph. Suppose we have one binary matrix. I have taken a simple identity matrix of order 3. Then if we construct some portion of the adjacency matrix with that identity matrix, we shall get one subgraph like this. Now come to the idea of partial transpose. Partial transpose was first introduced in the study of quantum entanglement. Suppose we have one density matrix as we write in equation 6. Then partial transpose with respect to the second subsystem will be like that. We shall change the position of K and L. That will give us a new density matrix. Based on this process, we determine whether this particular density matrix will be separable or entangled, etc. Now, if we want to write this operation in matrix form, then we shall see that we are actually doing a transpose on the individual blocks. So the density matrix is partitioned into equal size blocks, and on each block we are taking a transpose. Just now I have discussed that when we are creating some partition on the graph, then we are actually creating some blocks in the adjacency matrix. Now, when we are taking the transpose on the adjacency matrix blocks, then that should be reflected in graph. So, the changes will be like that. Suppose in our graph there is a tilde edge. Suppose the edge is from V11 to V22. Then this edge will be altered to V21 to V12. Also, suppose there is a tilde edge between V22 to V1m. Then after partial transpose, only this tilde edge will be changed from V12 to V2m. And those edges, which are either horizontal or vertical, will not change. We shall just change the tilde edge. That is the graph theoretic counterpart of partial transpose. So when we are doing partial transpose on matrix, we are taking a transpose on the individual blocks. And when we are taking partial transpose on graph, we are changing the position of tilde. If we do this operation on graph, we shall see that the transpose is done on the adjacency matrix. When we are doing the partial transpose, there is no change on the vertex set or on the labeling of the vertices. Also, there is no change on the horizontal or vertical edges. Now, based on graph theoretic partial transpose, there are several articles. I have listed here only 4, but actual number will be 5 or 6 times more than that, where they are using the partial transpose to investigate quantum entanglement, where the density matrix is connected to the graph. Now, there are some graphs which we cannot change in partial transpose. In those graphs, there are no edges which are tilde. We have either horizontal edge or vertical edge. Then this graph will not change. We call them partially symmetric graph. Suppose there is a tilde edge between V12 or V21, then there is one tilde edge between V11 and V22. That means if we change those tilde edges, this effect of the change will not make any kind of alteration in the graph. So those graphs don't change in partial transpose. We call them partially symmetric graph. This idea of partial symmetric graph is different from the original idea of symmetry in graph. Suppose in this figure, this is not a symmetric graph, but we can define the vertex labelings on it in such a way that this graph will not be changed after partial transpose. So this portion I have just taken here. So there are some asymmetric graphs which are not partially symmetric. Also we can find some partially symmetric graphs which will not be symmetric. So these two ideas are not. So there are some graphs where the graph G and its partial transpose are isomorphic. Suppose this one and this one. These two graphs are isomorphic, but this graph is generated after removing this tilde h and adding its counterpart. Same as here. These two graphs, G and G transpose, are neither isomorphic nor they are cospectral for their adjacent symmetric sets. This graph and this one, they are not isomorphic, but they have same eigenvalues with respect to their adjacent symmetrics. Suppose we have two graphs, G and H. Both of them are isomorphic. But after partial transpose, the new graphs need not be isomorphic. So graph isomorphic, the partial transpose has such type of characteristics. Now, this partial transpose is a different idea from the Godsil-Mackey switching. That is a very familiar, well-known idea to construct cospectral graph. Suppose we have this graph G. This is partitioned into two parts. This is one partition, another is this one. If we do the Godsil-Mackey switching, we shall get the first graph. But if we do the partial transpose, we shall get the second graph. In the next section, we shall construct some cospectral graph using partial transpose. We find that if we do partial transpose on a bipartite graph, then the new graph will also be isomorphic. So they have same eigenvalues. We can generalize this fact also. Suppose we have considered this graph where the induced subgraphs by V1 and the induced subgraphs by V2 are isomorphic with the identity mapping. Then we can find that after partial transpose, the two graphs, the original graph and the partially transposed graph, are isomorphic. As they are isomorphic, they have same sets of eigenvalues, so they are cospectral. But if the two sets, the V1 and V2, are not isomorphic, or they are not isomorphic by the identity mapping, then the two graphs, G and its partial transpose, will not be isomorphic. So that time they might have some different eigenvalues. As I have considered here, the graph G, it has two induced subgraph for V1 and for V2. They are isomorphic, but the isomorphism is not the identity isomorphism. In that case, the graph G and G partial transpose is not isomorphic, or they are not cospectral. There is an easy process to construct cospectral graphs. Suppose in the adjacency matrix of the graph, if we keep some commuting normal matrices, then we can prove that the graph G and its partial transpose will be. So when we have a family of commuting normal matrix, we can prove that there is some non-singular matrix, capital X, such that we can write AI transpose is equal to X inverse AIX. In fact, this fact we can use to prove that the graph G and its partial transpose have same spectra. This proof is much easy to discuss. When we do partial transpose on the graph, we take a transpose on the individual blocks. So the adjacency matrix of the new graph has this form. Now, for all the block matrices, they are each a non-singular matrix capital P, such that Aij is equal to P inverse Aijp wholes. Now, the second equation we can break into three different matrices in this way. So the matrix here is the adjacency matrix of the original graph. P is a non-singular matrix. So the identity matrix tensor product P will also be a non-singular matrix. Therefore, the adjacency matrix of original graph and the adjacency matrix of the partial transpose has the same set of eigenvalues. This is not mandatory. Suppose consider this graph G and its partial transpose. Both of them have same sets of eigenvalues, but the block matrix, this one, is not a normal matrix. We can construct large families of cospectral graphs. Two procedures we shall discuss here with some examples. Suppose consider two graphs which are isomorphic and which are not isomorphic and they have same set of eigenvalues. One is G, another is G partial transpose. If we check the adjacency matrix of G, we shall get this matrix. And G transpose has this adjacency matrix. Now, the matrix P is like this one. If we multiply P inverse and P with any of these blocks, we shall see that we shall get the transpose of that block. These blocks we can use to construct a bigger matrix. So from these two graphs, we can construct the graphs like this one. We have just taken the same block in another part. Then this graph and this one will have same sets of eigenvalues. Similarly, if we add one an identity matrix, then also the new graphs will have same eigenvalues, but they are not cospectral. Also, we can add some new vertices in the different partitions of the graph. Suppose we have G and G partial transpose like this one. We can add one new vertices to each partition of G. Suppose this one. We have just taken a mirror reflection along this line V12, V22, V32. The new graphs will also be non-isomorphic and they have same sets of eigenvalues. Partial transpose is also useful to construct non-isomorphic signless Laplacian cospectral graphs. So for that we have to introduce the characteristic polynomial of a signless Laplacian matrix. We can express the coefficients of the characteristic polynomial in terms of TU subgraph. TU subgraph means tree and unicyclic graph. One graph is called a unicyclic graph if it has only one cycle in it. Suppose here we have only one cycle in the graph, so this graph is called a unicyclic graph. Suppose the characteristic polynomial of the signless Laplacian matrix is like this one. Now these coefficients P0, P1, etc. we can write in terms of TU subgraph. The formula is like this one. Suppose in a spanning TU subgraph, we have C number of unicyclic graphs and different trees, T1, T2 up to Ts. Then the weight of the TU subgraph we can write in this way. And when we are writing the coefficient P1, P2, etc., then also we can write them in terms of these weights of the TU subgraph. Suppose in this case we have the graph G and its partial transpose. Here in both the graph we have TU subgraph of one edge is 3. Suppose in the graph G we have 3 trees. One is V1, V2, second one is V1, W1, third one is V1, W1, etc. So where is the change? Here is no cycle, but here is a cycle. Now if we check this formula, here is 4 to the power C and here is 1 plus mod of ETI, means number of edges in the graph Ti. So here we see that when we are considering the TU subgraph with 3 edges, for the first graph there is no cycle, so its weight will be 1 plus 3, 4. And the second graph, here is only one cycle, then its weight is also 4. Although these two graphs are not isomorphic, due to there is no change in the edge weights, so the characteristic polynomial will be same. When they have the same characteristic polynomial, they have same sets of eigenvalues. Now, several sets of graphs we can construct. Here, when we shall construct the graph, we have to keep this one in our mind, that we shall replace the unicyclic graph with a tree, and this tree has 4 vertices. Suppose here we have the cycle V2, V3, V4, etc. So we shall replace this cycle with a tree. This tree will be V2, W2, V2, W4. Whatever we have done in this picture, this we shall reflect in the new graphs also. That is the key point to note here. Here the two graphs has same characteristic polynomial. One graph has no tree, only one cycle. Another graph has no cycle, but it has tree. When we shall calculate their weights are same. Same fact we are using here also. One graph has a cycle, another graph has a tree, but they have same contribution in the characteristic polynomial. As the two characteristic polynomials are same, they have same sets of eigenvalues. Larger graphs from smaller graphs, by adding a number of additional edges in it. Suppose we have construct one pair of graph which are non-isomorphic and cospectral, and we can find them by partial transpose. The first two, this one and this one. Now in these two graphs we are adding some edges. One is from V2 to V5, and this same edge we are adding in the another partition W2 to W5. This way we can increase the number of edges in the graph. In all the cases we shall see that the new graphs will be cospectral to their partial transpose. Also, in the between the two partitions, we can add some new edges. We have to maintain one condition, that when we are adding the new edges, then the new subgraph will be partially symmetric. Recall that a partially symmetric subgraph is unchanged when we do partial transpose. If only that much criteria is satisfied, then we can find that the new graphs will be cospectral to their partial transpose. So that much work I did in two of my articles, and there are several problems which we can try in future. Suppose there are many pairs of cospectral graphs which are not determined by partial transpose. These two graphs I have given here, both of them had same sets of signless Laplacian spectra, but we cannot find any vertex labeling on that such that one graph is partial transpose to the another one. But the best problem to attempt here to apply the idea of partial transpose in quantum state transfer. Suppose we have one graph such that if we subtract two vertices A and B, then they will be cospectral. Then we can do a perfect state transfer from A to B. Much work is done in this direction. If we can apply the construction of cospectral graph using partial transpose, then it might be interesting. Thank you. I had only that much to share with you. I am worried if you can follow my accents. It might be a bit different from Canadian English.
Thank you for a very interesting talk. Do we have any questions for the speaker? Okay, so I have a question. So we use the partial transpose to construct cospectral graphs, right? What can you say about the complements?
What about its complements?
Yeah.
No, it completely depend on the particular labeling on the vertex set which you are using. So when we are constructing the new graph, then we have to think about the vertex labeling in that. So there is no direct connection between these two.
Okay, there's no other question, then let's take the speaker again.